Hello students, in continuation with my lecture for relativistic mechanics, I have briefed you about Michelson-Morley, negative results of Michelson-Morley, inertial and non-inertial frames of reference, and what a frame of reference is. Now today, the two postulates of special theory of relativity and Lorentz transformation equations. Now, Galilean transformation equations, which were very simple, and I'm sure you can recollect, x is equal to x dash minus vt and y equal to y dash, z equal to z dash and t dash equal to t. They failed to explain certain concepts of relativity. Now, Lorentz developed proper transformation equations, and along with that, he specified the fact that velocity of object under observation in relativistic mechanics should be approximately the speed of light. It should not be very much less than speed of light. Otherwise, relativistic mechanics concepts and his equations will fail in many conditions. So, once again, we begin by deriving this question. This comes as a 10-mark question in section C. Derive Lorentz transformation equations and under what conditions they get reduced to Galilean transformation equations. So how are we going to start the answer? We will first draw our two frames of reference, as I explained you in the previous lecture, S and S dash. We will take any point P under observation. P will have coordinates x, y, z, and t with respect to frame S, x dash, y dash, z dash, t dash with respect to frame S dash. Now, let these two frames, the frame S dash, move with velocity v relative to stationary frame of reference S. And then what happens is the transformation equations needed a change so that they could be accepted. Let us correlate this transformation along the x-axis as x dash is equal to k into x minus vt, where k is a proportionality constant and we have to derive the same. So a bit of mathematics is involved in finding out Lorentz transformation equations, because Galilean transformation equation said x dash is x minus vt simple. This failed to explain certain concepts. So now some change Lorentz did in this expression. Let us assume that change to be k. And now we will find out what was k. So from Einstein's first postulate, which stated that laws of physics are same in all frames of reference, that is, if it can be taken either in the same direction or in the opposite. So x becomes equal to k into x dash plus vt dash. This is just a direction change. Now, what we have done, this x dash value we have put here. So x becomes equal to k into x dash is this much, k x minus vt, we put it here. We open the equation and make it more simple, looking like t dash equal to kt minus kx by v into 1 minus 1 upon k square. Einstein's second postulate stated that velocity of light is same in both frames of reference. That means it is c, that is 3 into 10 to the power of 8 meter per second. And from mechanics, we know the formula, distance is speed into time. So x is equal to ct in my original frame of reference and x dash is equal to ct dash. C will remain same in both the cases. Putting this value of x and x dash in this equation above here, we get c dash, ct dash is equal to kt into c minus v and ct is equal to kt dash into c plus v. Here. Then multiplying equation 4 and 5, we get this expression. We take c square terms on one side, k square, which we have finally trying to find out on the other side. and we get it simplified as k equal to 1 upon under root 1 minus v square by c square. Putting this value in the expression for t dash, we get t dash, and then putting the value of k as 1 upon under root 1 minus v square by c square, x dash is equal to x minus vt upon under root 1 minus v square by c square. T dash is t minus vx by c square under root 1 minus v square by c square. The relative motion across y dash and z dash has been assumed as having no change. These four equations were known as Lorentz transformation equations, and now have a look at it more carefully. These equations will hold true only till the time velocity of object under observation is traveling with approximately the speed of light. If this doesn't hold true, then these Lorentz transformation equations will get back to Galilean transformation equations. This is what was asked in the question. And now have one more closer look to the fact that this is under root 1 minus v square by c square. That means if v becomes greater than c, that means velocity of light becomes velocity of object or the other frame becomes greater than the speed of light, this expression will turn out as imaginary, because under root of a negative quantity becomes imaginary. Then again Lorentz transformation equations will fail. We cannot solve imaginary quantities. Next, if v is very much less than c, then we can neglect this ratio, because subtracting 1 minus say 0.00001 is useless. We will take the approximation and we will make it under root 1. So under root 1 is 1. So again, this Galilean transformation, it will get back to the original Galilean transformation equations. Hence, the criteria for making me acceptable to Lorentz transformation equations is that velocity of the body under observation should be traveling with approximately the velocity of light. If it becomes very much less than the velocity of light, then they will reduce to Galilean transformation equations. So in order to fetch 10 marks in your AKTU exam, this much is the answer you should be writing. This diagram will fetch you around 4 marks. These steps will give you 3-4 marks, and then the conclusion, Lorentz transformation equations and under what conditions they reduce to Galilean transformation equations. If we have to take the inverse side, just replace minus by plus, x dash plus ut upon under root 1 minus v square by c square. Now, proper length. The length of a rod by an observer in the frame in which the rod is at rest will be called its proper length or actual length. This is the amount of length contraction an object suffers if it is kept in the frame where it is traveling with approximately the velocity of light, known as length contraction. So now I will explain you length contraction first, then I will explain you these numericals. Length contraction. It means that suppose I take the length measured by an observer in stationary frame with respect to the length measured in the, take 2 frames of reference, S and S dash. Let the value in stationary frame be x1 dash and in the moving frame it be x2 dash. Then to human eye, this length will appear contracted the moment this frame S dash starts moving. How? You see stars and sun from the surface of the earth, they appear so small, but that is not their actual length. They are much, much bigger than what they appear to the human eye. You see an aeroplane standing at the airport. When the aeroplane is on the airport, you observe its actual length. The moment the aeroplane starts flying high up in the sky, with you standing in the inertial frame of reference and aeroplane in the non-inertial frame of reference, slowly you observe a decrease in its length, and ultimately it is not visible. So this decrease in length is known as length contraction, and very simple way of finding out the formula is x2 dash minus x1 dash. From Lorentz transformation equation, just keep the value of x1 dash as x minus vt upon under root 1 minus v square by c square, and x2 dash keep it as x2 minus vt upon under root 1 minus v square by c square, and you get an expression for length contraction. You can automatically make yourself comfortable, if you know much of mathematics, that under root 1 minus something will be a very small fractional quantity. So obviously, suppose if a meter rod is appearing 8 meter to me on earth, and if it is taken to another frame which is traveling with approximately the velocity of light, then this length will get shortened because I am multiplying it by some quantity less than 1, that is fraction. So this automatically turns out that the length observed is shortened than its actual length. Okay. Similarly appears smaller than the length when is it at rest with respect to the observer. This is known as length contraction. This numerical has been asked many times in your AKTU paper. Let us solve it together. Find the length of a rod moving with a velocity of 0.8 c. What is c? Speed of light. You don't need to right now put in the value 3 into 10 to the power of 8 meter per second. Just wait. It will get cancelled when you put the value in the equation. In a direction inclined at 45 degree to its own length, proper length of rod is given to be 60 centimeters. So now we are going to take variation only along the x direction. So from vector analysis, we know that the x component from vector analysis, x component is taken by the cos term, and the perpendicular component, which we don't require, is taken by the sine. So Lx, that means across the x-axis, is equal to L cos 45 degree. Cos 45 degrees 1 upon root 2. So Lx is equal to L upon root 2. Length of rod in the y direction, Lx dash is equal to Lx into under root 1 minus v square by c square. Putting the values we have been given in the equation, v has been given as 0.8 c. So if I put 0.8 c here, c square get cancelled, and I am left with L equal to L upon under root into 0.6, that is approximately 0.4 L. For resolution of vectors, the final L will be equal to under root Lx square plus Ly square. So Lx is 1 upon root 2 and Ly is 0.4 L. Putting these mathematical values, I get the answer. Similarly, this numerical has also been asked many times, that if a spaceship is 50 meters long and it were to pass the Earth traveling at 2.4 into 10 to the power of 8 meters per second, what would be its apparent length, assuming LT transformation equation. So this length which we have been given is the original length. So we will put 50 here, under root 1 minus v square. V has been given as 2.4 into 10 to the power of 8, and c is 3 into 10 to the power of 8, and we get the answer. Similarly, there are other numericals. You can take the PDF from the comment box which below my video lecture and solve them for your further practice. Time dilation. Let me give you a practical example. Suppose right now in India, the time is 7:30 p.m. Then this same time will not be there in Australia or any other place across the globe. If we travel across the globe, the time will be different. This is known as time dilation. Relativistic mechanics also take into consideration time dilation because of relative motion in both the frames of reference, that is inertial and non-inertial. Or relative motion affects the measurement of time also while traveling. Suppose you are traveling and you are traveling to states from India, then the time clock there will be different from what it is showing in India at a specific time. So a clock in the stationary frame measures longer time interval between two events occurring in moving frame of reference than a clock in the moving frame. So for this again, we take two frames of reference, two clocks have been drawn just to show you time dilation effect. And now we will find out the real T naught is equal to T2 dash minus T1 dash. From Lorentz transformation equations, we know that T is equal to T dash plus x1 V by C square divided by under root 1 minus V square by C square. The two time clock observed by an observer in S frame are T1 is equal to T1 dash plus x dash V by C square upon under root 1 minus V square by C square. T2 is equal to T2 dash plus x dash V by C square divided by under root 1 minus V square by C square. We subtract both these equations to get an expression for time dilation equal to T is equal to T naught upon under root 1 minus V square by C square. Time is dilating for a moving observer is proved by this mathematical observation. A clock moving with uniform velocity relative to an observer appears to him to go slow by a factor under root 1 minus V square by C square than when at rest relative to him. This effect is called time dilation. Once again, the very same conclusions which I told you in length contraction right now. Again, have a look at this formula. Under root 1 minus V square by C square. If V is very much less than C, then V square by C square will be neglected and there will be no time interval. If V is equal to C, then time will be undefined or infinite. That means it shows that a clock moving with speed of light will be appeared to completely stop for an observer in stationary frame of reference. Very same conclusions. This expression will also hold valid only till the time velocity is approximately equal to velocity of light. Time dilation, two very common events. They have been asked in a gap of 4-5 years, what do you mean by twin paradox or existence of new meson on Earth's surface? They give a numerical on this topic. Twin paradox. A moving twin in space estimates the age of his twin on Earth to be shorter as he is treating himself in an inertial frame and says that his twin brother on Earth is moving in opposite direction. So the time should dilate for him. Similar observation will be given by his twin brother. Mu mesons are cosmic ray particles produced in the atmosphere at a height of 10 kilometers from the surface of Earth. So the lifetime is found to be 2 into 10 to the power of minus 8 seconds and their speed is 2.994 into 10 to the power of 8 meter per second. Distance traveled turns out as 600 meter, but these particles are found on the surface of Earth, which indicates that they are actually traveling a distance of 10 kilometer, not only 600 meters. So this will be possible if time dilation is considered. Due to time dilation, lifetime of particle is obtained as 3.3 into 10 to the power of minus 5 seconds. That means approximately 3.33 microseconds. So distance traveled is 10 kilometer. But these particles actually travel around 10 kilometers to reach the Earth's surface before diminishing. So this is also a very good example of time dilation. This numerical is asked many times. At what speed should a clock move so that it may appear to lose 1 minute in each hour? Since clock is losing 1 minute in every hour or 60 minutes, so 1 minute or in 1 hour. So 1 hour has 60 minutes. Hence, it must record losing 1 minute. So 60 minus 1 is 59 minutes for 60 minutes recorded by a stationary observer. So T naught becomes 59 and T becomes 60. You get the ratio. C is speed of light, 3 into 10 to the power of 8, and you get the answer for V. See, mu meson numerical has been asked. A certain particle called mu meson has a mean life of 2.5 into 10 to the power of minus 7 seconds. What is the velocity of mu meson if its proper time is 2.5 into 10 to the power of minus 8 seconds? From Lorentz transformation equation, we know that del T is equal to T naught upon under root 1 minus V square by C square. Del T has been given to us as 2.5 into 10 to the power of minus 7 seconds, and del T dash is 2.5 into 10 to the power of minus 8 seconds. So we put these values here in this expression. This is a very simple equation. Cross multiply, square on either sides, and you get the answer. A clock keeps correct time. With what speed should it be moved relative to an observer so that it may appear to lose 4 minutes in 24 hours? T is equal to T naught upon under root 1 minus V square by C square. Now, 4 minutes in 24 hours. That means we will first convert these hours into minutes. So 1 hour is 60 minutes. So 24 into 60 is 1440 minute. And moving with the clock, it appears to lose 4 minutes. So we will add 4 to this and we get 1,444 minutes. And we put these values in my time dilation expression, and we will neglect the higher order terms when we open the binomial expression, and when we get the answer for velocity. Other numericals you can practice from the PDF which I am giving in the drop down box. Thank you.